Okay, so let us see the fourth section now, ideals and quotient rings. Now we have already come across the idea of homomorphism between two rings and its kernel. So the next thing we would like to do is to define a normal subgroup analog in rings. We already know the concept of a normal subgroup of a group from group theory. We want a corresponding concept in rings. So let us now recall some group theoretic things. Suppose two groups are given to us, or say a group is given to us and we have a normal subgroup n also given to us of this group. Then we know that there is a homomorphism whose domain is G, range is G by n. This homomorphism is onto, and what is that homomorphism, by the way? It maps an element into the coset Gn, or you can write Ng also. They are the same thing because n is normal. So every left coset equals the corresponding right coset. This map turns out to be I think I need ink. Okay, give me some moment. So we know that this, from group theory, we know that this map is an onto homomorphism with kernel n. So if a normal subgroup is given to me, then it turns out to be the kernel of some homomorphism. Conversely, if I have a homomorphism of one group into some group G prime, then the kernel of that homomorphism is a normal subgroup of the domain group. So like this, in group theory, the concept of normal subgroup turns out to be equivalent to the concept of kernel. Now in rings, we already know about kernel of a ring homomorphism. Now can we use this idea to define a normal subgroup analog for rings in such a way that whatever we define for rings, that ultimately turns out to be kernels of ring homomorphisms. Just like here, normal subgroups are kernels of group homomorphism. In fact, this is true, we can do it, but in what way shall we do it? You see, when we define a normal subgroup, the definition does not involve any homomorphism, any group homomorphism. In fact, it's defined like this. There are several equivalent definitions, but the first one arguably is this one. If we have a subgroup n of G of some group, then n is said to be a normal subgroup if we choose any element from the group G and any element from the subgroup n, then this implies G and G inverse again belongs to N. This is the definition of a normal subgroup, for a subgroup to be a normal subgroup. So it does not involve any homomorphism. We cannot see any relation to any homomorphism, that idea. However, later on it turns out that that is the case. They turn out to be kernels of homomorphism. Now, what should the corresponding thing for rings be? So that thing is, we can take our cue from one of the results that we have proved in the previous videos, is this lemma 332. So what this lemma basically said is this: if we have two rings R and R prime, and phi is a ring homomorphism, then its kernel has two properties. The first is that this is a subgroup of R under addition. And the second property says that if we choose any element from the ring and any element, say, let me call it B, from the kernel, or I think we chose A in the kernel and R in the ring, then both the elements AR and RA belong to the kernel. Now note that although this result involves a homomorphism, but these conditions don't involve any homomorphism. In place of I phi, if we have a set, then also the conditions make sense, and that's what we are going to use to define the concept of a normal subgroup analog for rings. And that's where this next definition comes. And so we have the first definition of this section. So this is the definition of an ideal. The normal subgroup analog will be called an ideal, or some of you may already know about that. So a non-empty subset U of a ring R is called a two-sided. Two-sided is written within brackets. We will we will see why it's written like that. Is called a two-sided ideal of R if the following conditions hold. A. U is a subgroup of R under addition. You see, we are mimicking the first property here with I phi replaced with U. And B, if R belongs to R and U belongs to U, then both UR and RU are in U. So here also we have mimicked this one. So such a set will be called an ideal of R. So because of this definition and because of this lemma from the previous section, we automatically know that every kernel of the kernels of homomorphisms are ideals in the domain ring. Okay. Now let us talk about that word two-sided. Condition B says that U swallows up multiplication from the right and left by ring elements. You see, if we are multiplying any element of U from the right side by a ring element or from the left side by a ring element, then U swallows up that multiplication. The result is again in U. That is why we call an ideal two-sided. Okay. Now there are some concepts where we have only one-sided ideals. I mean, they are not, of course, ideal in this sense, but they satisfy only one of these conditions. One of these conditions means, of course, they satisfy the first condition. All of them are additive subgroups of the ring, but some of them only satisfy the condition that if you multiply their elements by ring elements from the right, then those products belong to the set. They are called right ideals. The corresponding one involving the other one are called left ideals. Now these concepts, these derivative concepts of ideal, we will not need anywhere in this book other than the some of the exercises. So we don't bother to call ideals two-sided. We will simply call ideals. Let's just write that. Since we shall not need any derivative concept of ideals, left or right ideals. Other than in some of the exercises. For us, ideal means, or ideal will mean, two-sided ideal. Okay. So this is our normal subgroup analog in a ring, that is ideals. Right. Now, next, what shall we do with them? Next thing, of course, we have to have a construction that we had in group theory, that of quotient groups of a group by a normal subgroup. So now that we have the concept of ideals, we are going to try to construct some sort of quotient ring of a ring by an ideal. So that's what we are going to do next. Okay. So let U be an ideal of a ring R, right? Since U is a subgroup of R under addition. That's the first condition, right? And R is an abelian group. R is an abelian group under addition. U is a normal subgroup. Since the group R is abelian, under addition, of course, under addition we are considering these things. Group structure is there under addition. Since R is an abelian group, in an abelian group every subgroup is normal. So U is normal. So that means we can form the quotient group R by U. So we have the quotient group R by U of all the cosets of U in R. That is, not that we are saying cosets, because of this abelianness or normality of U, left and right cosets are equal. That is, R by U is the set of all cosets. We can now simply write coset, but note that since our binary operation is addition, so instead of writing AU, we are going to write A plus U, because now the operation is there and it's written as plus, where A is any element in R. The binary operation on R by U is defined as follows. For two such cosets in R by U, their sum is defined to be this. And we already know these things. This just, it's from group theory, only the notation is changed somewhat because now we have addition. Okay. So now we have this thing. Note also that this is abelian. Why? Because the additive group R itself is abelian, so the quotient group is also abelian. This operation is abelian, so whether you add this to this or this to this, they are the same. Now we want to turn this thing into a ring, so we now need a multiplication. So next, we define a multiplication on R by U for A plus U and B plus U in R by U. We are going to define their product. And we define it to be equal to AB plus U. Now note that we are dealing with cosets, and we already know from group theory that a single coset have many different representations. This A plus U may be written as A prime plus U, where A prime is not equal to A, but the cosets are equal. So we have to be sure that what we have defined here is actually well defined. So for that, we now verify that this operation is well defined. Okay. Let A plus U, A prime plus U, B plus U and B prime plus U be in R by U such that A plus U is equal to A prime plus U and B plus U is equal to B prime plus U. Then A minus A prime and B minus B prime, both of them must belong to U. Then only these cosets will be equal. Okay, it's an equivalent condition for these equalities. Now we use the fact that U is an ideal. Since U is an ideal of R, we have A minus A prime times B plus A times B minus B prime, or no, it's not A times, it's A prime. This belongs to U. Why? You see, this is an element in U. So we can multiply this element from the right by a ring element B, and the product will belong to U, because U swallows up multiplication from the right. Like that, U swallows up multiplication from the left. So I can multiply this element of U by A prime. So that will also be in U. And their sum, of course, will be in U, because U is an additive subgroup. But this element A minus A prime times B plus A prime times B minus B prime, after simplification, after manipulation using the elementary ring properties, this turns out to be equal to AB minus A prime B prime, because A minus A prime B and plus A prime B, they cancel out. Hence, AB minus A prime B prime belongs to U. which implies a plus u times b plus u, which is nothing but ab plus u. This is equal to a prime b prime plus u. From this one we have this equality, and this is equal to a prime plus u times b prime plus u. So that's why this product that we have defined is well defined. Hence, multiplication is well defined. Okay, now the next we have to of course verify the other ring properties. Although they are easy, but for the sake of completeness I will show them. What else do we need to show? There are only two things we need to show. One is the fact that multiplication is associative, and the other is it distributes over addition, the addition in R by U. So that means we will need three elements. Then we have these following things. First of all, a plus u times b plus u times c plus u. This, according to our definition of multiplication, is ab plus u times c plus u. This is equal to ab times c plus u. Note that the product that we see here, this is the multiplication in the ring R. Okay, and we know that that multiplication is associative because it's a ring multiplication. So in place of this we can write a times bc plus u, and that is equal to a plus u times bc plus u, and this then becomes so this proves that multiplication in R by U is associative. Next, we verify the distributive laws. Next, a plus u times b plus u plus c plus u. So here we are attempting to verify the left distributive law. So this is equal to a plus u times b plus c plus u. This is by the definition of addition in R by u. Now by the definition of multiplication, so you can see that the calculations are almost mirroring those in R, the corresponding calculations in R. That's why everything is happening so smoothly. Now, using the ordinary left distributive law that is available in R, this is equal to AB plus BC plus U. So this becomes AB plus U plus BC plus U. And this can be written as A plus U times B plus U plus A plus U times C plus U. So that's how we get the left distributive law. And Now we verify the right one. It's similar, but let's just go through it. A plus B plus U times C plus U. And this is equal to A plus B times C plus U. So using the right distributive law in the ring R, this becomes equal to AC plus BC plus U. AC is equal to AC plus U plus BC plus U. Hence, the left band are true in R by U. So R by U is a ring. Now there are two more things that can be said about this ring. Or okay, first of all, let us say what it is called. R by U is called the quotient ring of R by the ideal U. Just like quotient groups are sometimes called factor groups, quotient rings also are sometimes called factor rings. Okay, now comes some conditions. If R is commutative, note that we have constructed the quotient ring for any ring R and any ideal U of R, but it may be the case that R is commutative. Then for any two elements in R by U, we have A plus U times B plus U by definition is AB plus U, but this is also equal to BA plus U because now R is commutative, so AB equals BA, and this again is equal to B plus U times A plus U. So that means the multiplication in R by U also becomes commutative. That is, R by U is also commutative. And one more thing is that if our ring R has a unit element, then so does R by U. If R has a unit element 1, then it can be seen that 1 plus U is a unit element in R by U. It's very easy. you take the product of any one such product where one of them is 1 plus u. You can see from that itself that you will get back the other element. So 1 by u acts as the unit element of r by u if r has a unit element 1. Okay. And the other results that can be carried over from group theory also turn out to be true in this case. What are those results? One we have already mentioned today, and that is the fact that if we have a group G and a normal subgroup N, then there exists a homomorphism from G onto G by N. That means G by N is a homomorphic image of G. Image because this is onto, and homomorphic image because this is an image of a homomorphism. Image of G actually under a homomorphism. Just like that, if we are given an ideal U of R, then the quotient ring R by U is a homomorphism